Now, to resolve this, we instead try to model the underlying structure of the scene. And we do that by explicitly modeling the sensor acquisition itself, and thus taking these density variations into account in the probabilistic model. So when we applied our method to the same input as we saw before, this was the result that we got here, and we see that the point sets are nicely aligned. So I'm going to explain this more in detail in this presentation, but first we're going to look at a little bit of some background. So point set registration is a well-studied problem within computer vision. The task is simply to, given a number of point sets, to find the relative transformations between them. And in this work we deal with rigid transformations. And methods for point set registration can be roughly divided into two main classes of methods. So first we have the ICP-based methods, where you iteratively assume pairwise correspondences between the point sets. And then the transformation parameters are found by iteratively minimizing the distances between these pairwise correspondences. The probabilistic methods, on the other hand, they generate a probabilistic model of the point sets, and then jointly infer this probabilistic model with the transformation parameters, usually using maximum likelihood approaches. And one such method, or a state-of-the-art probabilistic method, is this JRMPC method, which was proposed in this ECCV paper, ECCV 2014 paper. And we base our work on JRMPC, on this framework. So I'm going to just briefly explain how JRMPC works here on this slide. So JRMPC stands for Joint Registration of Multiple Point Clouds. And differently from most ICP-based methods, JRMPC naturally generalizes to multi-view registration. So this shows basically how the algorithm works. So in this example, we have 4 point sets that we intend to register. The method then generates a probabilistic method over the joint distribution of the 3D points. And this is realized using a Gaussian mixture model. And the Gaussian mixture model parameters, together with the transformation parameter, are jointly inferred using a maximum likelihood approach. And this is carried through in an expectation maximization framework. And recently this work was also extended to also utilizing the color information in the probabilistic model in this CPPSR algorithm that was proposed in CVPR 2016. And we're going to use these methods as baseline approaches to our method. So, as we said before, these probabilistic methods, they struggle when there is variations in the point density in the point sets. And a common way of resolving this problem is to resample the point sets in order to obtain a uniform distribution of points. However, this will lead to sparsification of the point sets, and we will lose some structure by doing that, and that will lead to loss of accuracy. And another problem is that it's a difficult task to find the suitable downsampling parameters, and that might have to be tuned for every scenario. So we instead propose a density adaptive approach where we actually utilize all the points in the point cloud. So now to our method, which is the density adaptive registration method. So instead of modeling the spatial location of the 3D points, we intend to modeling the underlying structure of the scene. And we do this by first defining this latent scene distribution, which we denote by QV here. And we find QV by minimizing the KL divergence from QV to our probabilistic model, which we denote PV. And PV is again a Gaussian mixture model as before. And this is equivalent to maximizing the negative cross entropy, or as we denote here, our objective function. So the problem is now, so how do we optimize this objective function when this QV is unknown? Well, first, if we assume that the 3D points in the point sets are sampled directly from this underlying scene distribution QV, then we can perform a Monte Carlo sampling approximation of the objective. And by doing so, we get the following result here as in equation 3, which we see is simply the joint log likelihood. And that is, as we know, the common objective used in standard maximum likelihood approaches, as well as in JRMPC and CPPSR. So our point here is that the point do not actually originate from this latent scene distribution, but rather another distribution that has been induced by the sensor. And we denote this sensor-induced distribution by QX. And this is what we see here when we see these variations in the point density. Now, if we want to perform a Monte Carlo sampling approximation of the objective by sampling from QX instead, we have to modify the objective a little bit, as we do here in equation 4. And what we see here comes out is this function f, which will act as weights in this sum here. And we call this function f the observation weight function. And the observation weight function is simply the ratio between the latent scene distribution and the sensor-induced distribution. And it's quite easy to show that this objective can also be optimized using expectation maximization. So what remains now is to determine this observation weight function f here. And firstly, we assume that the latent scene distribution is uniform on the surfaces. So this observation weight function only depends on the local density, sampling density on the surface. So here we see an illustration of the sampling pattern from a sensor on a surface. And as we can see, the sample density both depends on the distance to the sensor and the local geometry of the surface. And with this in mind, we first derive a sensor-based model for the observation weight function, which is simply an analytically derived expression for the sampling density on the surface. However, this is a simplified model which doesn't take all the causes into account, such as specularities and occlusion, etc. So we also propose an empirical model where we base the observation weight function simply on the local statistics of the points. And it turned out in the experiment that this empirical model gave the best result, which is nice, since now our observation weight function will be independent on the sensor. We don't even need to know what kind of sensor has been used to acquire the point cloud in the first place. So here we see again the example that we've seen before, where we registered first using the CPPR algorithm, where we have used the maximum likelihood approach to infer the probabilistic model. And to the right here, we see the result after using our approach. And these black dots here, they denote the mixture components, or the means of the Gaussian distributions in the Gaussian mixture model, to illustrate how the probabilistic model looks like internally. So as we can see here on the maximum likelihood approach, the probabilistic model only focuses on the high density areas and almost ignoring the outer part here, the sparser areas. And in our case, on the other hand, the probabilistic model nicely actually describes the whole scene, which is what we wanted. So we perform experiments on a number of LiDAR data sets, publicly available ones, and we evaluate the angular error between the found rotations and the ground truth rotations. And I'm just going to show results from these VPS indoor data sets, which consisted of these 4 point sets. And we perform multi-registration on these point sets. So here's an example a typical example when we use the CPPR algorithm and on the raw point sets, and it clearly failed in this case. And on the same input using our method, we got this result, and the point sets are now nicely aligned. And this recall curve shows some statistics on this point set for multi-view registration, and each point on these curves, they correspond to the ratio of correct registration with respect to the threshold here on the x-axis. And we see here that the CPPR algorithm, which is the red curve here, has a very low recall on this data set. And if we perform resampling, we got the result here on the dashed curve. However, resampling required some significant tuning in order to obtain this result. And regardless of that, we still managed to have the highest recall on this data set, which is the blue curve here. And we show more examples and more comparisons in the paper if you're interested. So to conclude, we proposed a density adaptive approach for probabilistic point set registration. And we did it by minimizing the KL divergence between the latent scene distribution and our probabilistic model. And this was realized by introducing these observation weight functions. And we performed experiments on some challenging LiDAR data sets with significant variations in the point densities. And we showed improved results compared to resampling. So thank you, that was all for me. And hope to see many of you at the poster later on. Thank you.
Okay, we have time for questions. If you have, please go to the microphone here and there and speak out a question. who wants to break the ice of silence? Don't be shy. So then I break the ice one. So you're experimented on the LiDAR, say, from like Faro-like 3D scanner, as opposed to Kinect like moving scanner. Are there any difference? So you don't have much of density issues for those devices, but have you thought about testing it?
Yeah, exactly. So these settings, the RGB scenes doesn't have the same kind of density variations, and we tried some of it, and as you can predict, the difference was not as big as for the LiDAR settings, but yeah.
Then I have another one. Oh yes, question over here.
Okay.
Yeah. Hi. How do you determine the order of the mixture model? Like how many terms should be there?
How many? Can you say?
The components in the mixture.
How many components?
Yes.
Okay, so in the experiments we used the same number of components all over actually. So we didn't investigate this at all. So we used a fixed number, 200 components.
I think we have time for one more question, if anybody has. Yes. Every
How sensitive is it if none of the point clouds are, if the point clouds are not 100% overlapping? Let's say that they're like 10% overlapping or 20% overlapping.
Okay, it can handle some degree of non-overlap, but this is not at all handled in the algorithm. So, of course, if there's too less overlap, it doesn't handle it as well.
You didn't experiment with that, did you?
No, but that's something that would be really interesting to look into in the future.
Yeah, let's switch the computer. Let's thank the speaker again. Well, you are switching. If you are spotlight presenters, please come up in the first row. There's a number, and we have 3 missing spotlight presenters right now. So please come up to the front and have a seat. So next we have Zequn from Tencent AI Lab, and he'll take the ideas of left-right consistency in stereo and bring into the days of deep learning and use some cool DNA network, LSTM, to enforce the constraints.
So, hello everyone. My name is Zequn Jie, coming from Tencent AI Lab. I'm very happy to introduce our work, left-right comparative recurrent model for stereo matching here today. So first, let us recall what is stereo matching in 2 images captured by 2 rectified cameras. For each pixel in one image, we want to find its correspondence in the horizontal scan line in the other image. And the horizontal position difference between the pixel and its correspondence, we call it disparity. By stereo matching, we can obtain a dense disparity map for both images. Then using the disparity map, we can easily get the depth map by taking its reciprocal. So one important property of stereo matching is that the disparity map of both views are not necessarily the same, because when we scan all the pixels in the horizontal line, the correspondence pixel with the maximal similarity may not also find the original pixel as the most similar one. So such mismatching issues are quite common in the repeated textureless regions, and also the occluded areas and the complex object boundaries. So therefore, taking the information from the generated disparity maps of both views is a possible way to refine these regions and further improve the stereo matching performance. So we next quickly review the typical deep learning-based stereo matching pipeline. Usually we use a shared CNN to extract features for both left and right images. Then we use inner product layer or several free connected layers to obtain the matching cost volume. Then, but based on these cost volumes, we can obtain the disparity map by 2 different ways, either by using the winner-takes-all strategy or another disparity network to regress the disparity. So after we obtain the disparity maps of both views, left-right consistent check is performed to modify the values of the mismatching pixels with interpolation. However, previous such isolated left-right consistent check has several shortcomings. First, it relies on handcrafted inconsistency thresholding. For example, we may treat the estimated disparity difference greater than 2 pixels as inconsistency. Second, it refines the mismatching pixels disparity by local interpolation within a prefixed patch. For example, we may interpolate from the neighboring 8 or 15 pixels. Third, the disparity estimation model cannot take information from the disparity of the other view during both training and inference. So only an offline isolated left-right consistent check is performed. Instead of performing isolated left-right consistent check, we seek to achieve detect refine mechanism with the spirit of left-right comparison. So there are 2 key technical points. The first one is the confidence measurement. So by the online left-right comparison, we can obtain the confidence of prediction for all the pixels. Then use such learned confidence of prediction as attention guide. The model will selectively refine and update the disparity of the pixels with low confidence, which may be the left-right inconsistent ones. To achieve the goal of integrating left-right consistent check into the disparity estimation model, we propose a left-right comparative recurrent model. We call it LRCR model here. So this model requires the matching cost volumes of both views to be pre-obtained, and takes input the matching cost to generate the disparity of both views. We obtain the matching cost volumes of both views with the constant highway network. Then in the disparity estimation stage, at each recurrent step, the LRCR model will take the matching cost and the learned attention map at the last step simultaneously as input, then predict the disparity of both views with the stacked convolutional LSTM. Then the attention map at the current step can be generated by the left-right comparative branch, which receives both the predicted left and right disparity maps as input. So in this recurrent predict, compare, predict procedure, the disparity maps of both views can be progressively updated and become increasingly similar and accurate. Next, we take a close look at the left-right comparative branch. We have the predicted disparity of both views at the current step. We first warp the right disparity to the left view by sampling according to the predicted right view disparity value. Then we feed the left disparity and the warped left disparity to a small subnetwork by concatenating them as the input. And then the left view attention map can be automatically learned. For the right view attention map, it can also be obtained in a similar way. So one important thing about our approach we care about is that whether the pixels with high inconsistency are really the wrong predicted pixels. If not, using the learned attention map to guide the recurrent refinement will not work. So fortunately, pre-analysis found that the learned attention map is highly consistent to the real error map with respect to the ground truth disparity. Moreover, we find that the highlighted regions in the learned attention map are the repeated regions, like sky and the complex object boundaries, which show that the model can effectively learn the mismatching regions. So in the experiment, we first show the evolving of the predicted disparity, attention maps, and the real error map with the increase of the recurrent step. As can be seen, the attention maps are quite consistent with the real error maps for all the recurrent steps. Moreover, we also observe that both attention maps and the real error maps are diminished as the recurrent step increases. This shows the model can progressively make the disparity maps of both views more closer and more accurate. Next, we show some aberration studies. So here the experiments are conducted on Kitty 2015. We compare our model to a winner-takes-all strategy and the non-recurrent version model, which uses a feed-forward disparity network to predict the disparity, and the recurrent one without left-right comparison, which means it refines the disparity with only a single view result, and the left-right comparative recurrent version without attention mechanism, which means it directly gets the difference of the disparity of two views and use this map as the attention guide to for the next step refinement. We can find that the full version of the LRCR model achieves the best performance, while the version without the tension ranks second, and the single view recurrent model is the third, and the feed-forward disparity network ranks fourth. And the winner-takes-all strategy is the worst. Next, we also compare our model to the state of advance, including the lambda rest match, detect, replace, refine, and GCNet, which are all published in the CVPR of last year. The example here are the results copied from the online KT 2015 testing server. As can be seen, the result of our model looked best, and the result of the other methods may have many visible artifacts. This table shows the quantitative results of our model and the other state-of-the-art models on KT 2015. Our model is better than most deep learning-based methods, as well as lambda rest match, which is our baseline, but our method is slightly worse than the recently published end-to-end disparity model cascade residual learning. And on another two popular benchmark datasets, SimFlow and Midberry, our model also performs better than several existing methods, including winner-takes-all strategy, GCNet, MCCN, and lambda rest match. Next, we make some comments to our model. First, it is better than the other two-stage models, but slightly worse than end-to-end models. However, it has fewer parameters than end-to-end models. For example, compared to the recent cascaded residual learning, which has 17.5 million parameters, our model has only 13 million. Therefore, cascaded residual learning requires a large number of training samples to train the model well. And next, our model is slower than end-to-end CNNs due to the two-stage training and inference procedure. But we will also explore the feasibility of making the current LRCR an end-to-end model. Finally, to summarize, we propose a novel left-right comparative recurrent model which is capable of performing left-right consistent check and the disparity estimation jointly. And we introduce a soft attention mechanism as confidence measurement for better guiding the model itself to selective focus on the unreliable regions for subsequent refinement. And the results on KT, SimFlow, and the Midberry beat most state-of-the-arts. That's all. If you have any questions or more interest to discuss, please come to our poster, which is E11.
So we have 3 minutes of questions. Please come up to the microphone and speak out or raise your hand. Okay. Yes. Oh, over here. Filippo.
Hi. I was wondering if you have any insights on what happens in occluded regions, because the occluded regions cannot be made consistent on the left and the right side. So what does your model do there?
So for the occluded regions, as the one of you cannot have a ground truth or reliable prediction, so the left-right comparative branch can definitely identify these regions, right? Then these regions will be highlighted in the attention map, and so based on such a data-driven pipeline, and these regions may be more focused on the next step of refinement. So,
thank you.
Any other questions? Yes. Then I'll have one question. I have questions on the use of LSTM, the memory aspect. So you can do something similar by, say, belief propagation style, implemented in DNN, refining step by step without using memory aspect. I wonder if you have any Any thoughts on why LSTM memory-based? What does memory actually do?
I think the memory is used for recalling the prediction of the same view from the last step. Because as it is a refinement pipeline, we have to first check the initial prediction, and then based on the past prediction and do some refinement. So I think memory is quite important in this aspect.
Sure, you can come up with it. Any other questions? Maybe one more question if you have. Okay, let's thank that speaker again. So by the way, if you are spotlight presenters, please come to the first row. There's the numbers of the seat. We have 2 missing spotlight presenter right now. So please come and have a seat.
Good morning. Hello. Yeah. Good morning, everyone. My name is Yasser Sheikh, and I'll be introducing the last 2 talks of the session. So this talk is into Pano 3D, extrapolating 360-degree structure and semantics beyond the field of view. The authors are Shuran Song, Andy Zeng, Angel Chang, Manolis Savva, Silvio Savarese, and Thomas Funkhouser, and the presenter is Shuran Song, who will be starting in this fall as an assistant professor at Columbia University. Congratulations.
So hello everyone, I'm Shuran from Princeton University. So today I'm going to talk about our work on into Pano 3D, extrapolating 360 structure and semantic beyond the field of view. So let's start with a simple psychology experiment called boundary extension. So in this experiment, a subject is shown with a picture like this for a few seconds. And then the picture is taken away, and then the subject is asked to redraw the picture from their memory. And this is a typical result you can get from the subject. So at first, it looks pretty reasonable. But once you start to compare this drawing to the original picture, you will suddenly realize that the subject actually always draws 20 to 30% more beyond the boundary of the original image. And even if you start with a slightly zoomed-out version of this picture, you will still get back something look like this, where the subject starts to draw something that is completely not observed in the original image, such as the house or the trees. And this phenomenon happens almost all the time for every subject. And the powerful part of this experiment is that it demonstrates that we as humans have this incredible ability of imagining what's infer the contextual information about our surrounding environment beyond our observation, which is actually always limited by our field of view. And in fact, this ability of imagining what's beyond our field of view is also very critical for us in order to build a persistent understanding of our surrounding environment, supporting our spatial reasoning, and also performing tasks such as navigation and best view planning. So the question is, can we enable the machine to do the same? So in order to explore this idea, we studied the problem of view extrapolation, where the goal is to not only enable the machines to understand what they see through their camera, but also able to infer its complete surrounding environment beyond its camera field of view. So traditionally, when people work on this problem, they are mostly focused on predicting the appearance of the unobserved environment. In other words, they only focus on predicting the color pixels outside the image boundary. However, although this kind of output representation are great for visualization, they are actually really hard to be used directly to support high-level planning or reasoning. So instead, in this paper, we propose to directly predict the 3D structure and semantics of the unobserved environment. So by having this kind of output representation, the system will now be able to answer the questions such as, where can I move in this 3D environment, or where I should turn to find a door. And we call this task a semantic structure view extrapolation. So more specifically, given a partial observation of an indoor environment in the form of RGBD images, the goal of this task is to infer the complete 3D room with this 3D structure and semantic information. So in this example, our network predicts this room as if a bedroom with a bed in the middle, nightstand on the side, and a window on the wall. So note that the prediction actually includes the area that's directly behind the camera, which requires the system to predict something that is completely not observed in the input image. Indeed, it is a really challenging task, but our key idea here is that because the indoor environments are often highly structured, therefore, by learning over the statistics of many typical indoor environments, our model should be able to leverage the strong contextual cues inside the image in order to predict what's beyond the field of view. And more specifically, this task poses 3 major challenges, which also correspondingly shaped our approach to this task. So first is how we can obtain a large amount of training data for this task. Second, how we should represent the 3D structure in a way that is easy for the network to predict as output. And the third is how to provide a meaningful supervision for the network training, especially when the possible solution is not unique. So first, let's look at data. So in order to train a model for this task, we obviously need a data set that contains the semantic and 3D structure information for indoor environment. And it should also contain the whole room contextual information instead of just a single view image. And we also need a lot of them in order to cover the whole distribution of typical indoor environment. So based on these requirements, we make use of both synthetic and real-world 3D house data sets. So more specifically, we pre-trained our model on the synthetic data set, SunCG, and then fine-tune and test our model in the real-world data set, Matplotlib 3D. And in order to encode the whole room contextual information, we represent each 3D room by using a skybox panorama, where each pixel on the panorama is labeled with its color, semantic, and 3D structure information. However, different from color and semantics, where there are very standard data representation, it is actually not exactly clear what should be the best representation for 3D structure. So depth would be a very obvious option. However, it is actually really hard for the network to directly predict the depth value because it is highly viewpoint dependent and also tend to have a large variance even for the nearby pixels on the same 3D plane. And on the other hand, surface normal is much easier to predict because all the pixels on the same planar surface will share the same value. However, solving back the 3D surfaces from the surface normal alone is an under-constrained problem. So this also leads to the second challenge for this task, which is how to represent the 3D structure. So in this paper, we propose to represent the 3D structure using its plane equation, which basically decomposes the 3D surface into its surface normal and plane distance to the origin. So because all the pixels on the same planar surface will share the same plane equation, this representation is piecewise constant in any typical indoor environment, therefore makes the prediction much more robust. And here is a comparison result of using different surface encodings. So from the comparison, we can see that by using the plane surface encoding, our network is able to produce much higher quality 3D geometry. And after we encode all the 3D rooms with this multi-channel RGBD panorama, the goal of our network is then try to take in the panorama with missing region as input and then produce a complete panorama where the missing region are filled with semantic and 3D structure information. So the next important question here then is what kind of training objective we should use in order to train such a network. So as you can imagine for this task, there is a whole spectrum of possible training objectives. So on the one end of the spectrum, we can just ask the network to provide a prediction that is exactly the same as the ground truth on every pixels. And for this objective, we can directly use pixel-wise loss on each output channel. And on the other end of the spectrum, we can also ask the network to provide something that is possible, but don't need to match the ground truth at all, where we can make use of adversary loss for this objective. And more importantly, somewhere in the middle, we might still want the network to provide the prediction that is similar as the ground truth in terms of certain mid-level attributes, scene attributes, but not on every pixel. So for this objective, we actually designed several specialized loss functions in order to regularize the mid-level scene attributes, such as the scene categories and object distribution. where the object distribution laws basically encourage the correct prediction of object existence, but without penalizing on their 3D location. And our final model is trained with a combination of all these 3 levels of objectives that considers both pixel-level accuracy and global context consistency. And correspondingly, we also evaluate our algorithm's performance from these 3 different levels. So for example, we can use intersection over union and L2 distance to evaluate the pixel-level accuracy, and the probability over ground truth and Earth mover distance to evaluate the mid-level thing attribute, and also the inception score to evaluate the overall prediction quality. And for simplicity here, I'm only showing you the intersection over union for the semantic prediction, where higher is better, and the L2 error for the 3D structure prediction, where lower is better. And for the baseline algorithms, we compare to the nearest neighbor approach, and also the approach that first try to predict the color pixels for the unobserved environment by using an image in-painting algorithm, and then followed by semantic and 3D structure estimation based on the predicted color pixels. So from this plot, we can see that our model is able to achieve much higher accuracy in terms of both semantic and 3D structure prediction. So here I'm going to show you some of the example results of our method in action. So this is an input observation of an indoor environment with a missing region. And this is a predicted probability distribution of ceiling, visualized as a heat map overlaid with a ground truth image, where red indicates high probability and blue indicates low probability. And this is a prediction for floor, wall, bed. And this is the semantic labels with the highest probability for each pixels. And this is a 3D structure prediction provided by our network and also the ground truth rule. So from this prediction results, we can see that our network is able to predict the correct location of a bed as well as the partially observed chair. And our network also able to correctly predict the existence of a window, however, with a very different location compared to the ground truth. And on the other hand, our prediction also misses several objects, such as the pillows and the nightstands. And the final question that we want to ask in this paper is to see how well our algorithm compares to human performance on this task. So in order to see that, we ask different people to complete a 3D room based on a partial observation by using a 3D design tool. And here we show some of the example results that we gathered from 4 different users. And this plot shows the prediction accuracy of people in comparison to our approach and baseline approaches. So the horizontal axis shows the pixel distance for the observation, and the vertical axis shows the intersection over union. So from this plot, we can see that our algorithm is not as good as people, especially for the pixels that are far away from any observation. However, it's still significantly better than other baselines. So to sum up, in this paper, we introduced the task of semantic structure view extrapolation. And in our approach, into Panel 3D, we leverage a strong contextual prior by training our model over 2 large-scale house-level data sets, which is SunCG and Metapro 3D. And in order to leverage a strong geometry prior, we propose to encode the 3D surfaces by using 3D plane equation. And in order to provide meaningful supervision for the network training, we make use of multiple loss functions that considers both pixel-level accuracy and global context consistency. And finally, all the code and data is already available online, so please check it out and come to our poster for more detail. Thank you very much.
Thank you, Shuran. We have time, 3 minutes for a few questions. If you are interested, there are 2 microphones on either end. Please walk up. So I'll start with a question. One of the strongest claims in the paper, maybe is in the title, of view extrapolation. And it's interesting because machine learning methods tend to be poor at extrapolating, much better at interpolating than extrapolating. I wonder whether it's fair to call this problem extrapolation, especially since this is 360, and you actually do have 2 endpoints. So can you talk a little bit about why you consider this to be an extrapolation problem versus an interpolation problem?
Yeah, I think it's actually, especially in the context of a panorama, it's actually not very clear whether it's extrapolating or like interpolating. But we do test with different camera configurations in our paper. So sometimes we provide a panorama where the endpoint is visible, but sometimes the input is only one single RGBD image. So in that case, it's really just try to extrapolating instead of interpolating. Yeah.
One other question I had is that you define these three elements of your loss function, right? There's the L2 loss, which is trying to get to truth. There is the adversarial loss, which is trying to get to plausibility. And then you had your attributes in the middle. Can you talk a little bit about the importance of each one and what effect they played on the overall synthesis?
Yeah, so we in the paper we do some studies about each individual loss, what's their contribution, and I think one of the interesting findings that we found from the experiment is that actually this, if we just use, for example, L2 loss, it actually has a strong bias to big objects like floor, ceilings, and bed. But after we add those scene attribute loss and also adversarial loss, we start to see like more small objects are predicted in the extrapolation.
Right.
Yeah, thank you.
All right, let's thank the speaker one more time. So before we introduce the next speaker, once again, if the spotlight presenters can come and sit in front. I think there's still one missing presenter. If you don't come, we'll make things up during your spotlight presentation. All right, so the final talk is Polarimetric Dense Monocular SLAM. The authors are Luwei Yang, Feitong Tan, Ao Li, Chao Peng Kui, Yasutaka Furukawa, and Ping Tan. And the paper will be presented by Luwei Yang.
Oh, thank you. So good morning. My name is Luwei Yang. I'm from Funkhouser University in Canada, BC. So I will introduce our work today. It is called the PDMS, the Polarimetric Dense Molecular SLAM. So the motivation of this work is to solve the dense reconstruction for the featureless objects. So the featureless regions are challenging for the 3D computer vision algorithms. However, for many applications, the dense reconstruction for the featureless area is essential. For example, for the obstacle avoidance in the robotic applications, imagine a drone may head somewhere if it cannot see it or sense its 3D position. So to achieve this goal, we use polarization informations. Last year, precisely last year, CVPR, we present a polarimetric multi-view stereo where the data is captured with a DSLR camera mounted with a polarizer filter in front of the lens. This year, we use a novel camera. It is called the polarization camera. And we try to generalize the task of the multi-view stereo to the dense molecular SLAM. So the polarization camera has a different polarizer that embedded in front of each pixel in the sensor so that it can record multiple polarized images in a single shot. And in this way, we can capture polarized in video stream, and we can build a SLAM system upon it. So in the next, I will first introduce the physical model for the polarimetric 3D reconstruction. So basically, if we record multiple images while the polarizer is rotating, the intensity of the pixel will change over time, as you can see in the middle. And if we sample a pixel, this intensity changes, and that pixel will form a cosine curve with respect to the rotation angle of the polarizer. So here, we denote this phase angle of this cosine curve as angle phi. So this angle phi is very interesting as it can encode some shape information about the shape surface. So it is an angle between the projected surface normal and the x-axis of that image plane. However, this is only the case when the diffuse reflection dominates at that pixel. If it is the specular reflection dominates, the projected surface normal needs to be flipped for another 90 degree. So therefore, the phase angle here determines the projected surface normal up to a binary ambiguity. And we call this ambiguity as pi/2 ambiguity. So suppose we know the projected surface normal. It is possible that we can enhance the 3D reconstruction result. How? In particular, we can trace the so-called isodepth contour, which are locally perpendicular to the projected surface normal, as shown on the left side. The isodepth contour contains the pixels with same depth value. So this is a very important constraint and property. And as shown in the right, the blue arrows are the projected surface normals, while the red curves are the isodepth contours. We can propagate the depths of this by using the sparse reconstructed 3D points along these isodepth contours to get denser 3D reconstruction. So this is my pipeline. The input of our system are the image sequences with the corresponding phase angle map. And the tracking module first compute the camera pose for the input image sequences. Here we use a DSO for the tracking. And then for the initialization module, a rough surface was extracted for removing the ambiguity, as well as produce the initial seeds for later depth propagation. And given the inlier seeds, the depths can propagate it to the neighborhoods and will be optimized iteratively. And in the final step, we fuse the depth map into a triangle mesh. And the initialization and the iterative processing are our novel algorithm, and it takes 1.2 seconds to compute for each keyframe on a modern GPU. So let's talk about the first module. It is the initialization module. So here, we need to solve the pi/2 ambiguities. Here we use the isodepth contour constraint to remove the ambiguities. Specifically, we apply a local-based method where we first trace two isodepth contour along two directions, and we select one with less depth variation. So this method is very fast, but it has some noise, as you can see in the right side. So after the initialization, we start to propagate the depth map. So this process is called the two-view propagation and validation. So the depth propagation itself might generate some noise 3D points. So as you can see in this example, so in the left image, so we can see some noise white 3D points that near the book edge. So if you look at the references image, in the reference input image in the middle, you will see those white points come from the table. So we know that those positions are wrong in the left image. So if we propagate their depths along the isodepth contour, we will propagate the arrows. As you can see from the right image, so you can see all these flying contours or noise propagations. So in our previous work, we require a manual segmentation to avoid this propagate the outliers. And in this work, we propose a two-view propagation and validation strategy that could automatically remove the outliers. So here's our idea. We first start with the initial points. And we first propagate the depths using the current keyframe. And we do the same thing for the references keyframe. The references keyframe are selected from the previous image sequences. And we then do a consistent check to remove the wrong propagations. And as you can see here, the wrong propagation near the book edge has been wiped out, while the correct propagation on the table is maintained. So after multiple iterations, the inlier points can be propagated to cover a large regions. And as shown in the slides, the green pixels are the consistent points. So after the depth propagation, we use the propagated depths as a constraint and optimize the finite depths. Here, we are going to minimize this following energy function for the depth optimizations. So it has a data term as well as a smoothness term. For the data term, we have two error measurements. So the photometric error and another one is called the contour consistent constraint. For the photometric error, it is a very conventional photometric measurements that measure the two imaging patches, precisely the similarity of two imaging patches. And for the second one, the contour consistent constraint, it enforces the depths to be consistent along the isodepth contour. And we use a weight, it's called the spatially variant weight, to balance the two errors. So this weight is stronger on featureless area, while it will be weaker nearby the feature abundant area. So for the smoothness term, it also has two regularizers. So the first one is the conventional smoothness term, while the second one is called the phase angle regularizer. So it enforces the depth gradient direction to be consistent to the phase angle direction. So here we show some two results precisely. On the left is our input key frame. In the middle, we show a comparison of the traditional MVS multi-view stereo with our results on the right side. So in the right, we show the final fuse depth map. So here are some more examples. So at end of this talk, I will show a video demo. So here are some limitations for our current system. So the polarization camera we use is very preliminary, and it has a very low spatial resolution, roughly 700 by 600. And there is no auto exposure and auto focus. And the data transfer require an Ethernet port. And the power, and you also need external power or battery to power these devices. And furthermore, the SDK only support the Windows. So with all these limitations, the data capturing is tedious and very difficult, as you can see on the right side. So this is a real situation. We are trying to get some data. And for our algorithms, our algorithm has a large room for the improvement. So the depth propagation require good seeds to start with. And the overall algorithm assumes that the input light should be unpolarized incident light. So we propose a dense molecular SLAM for the featureless regions with polarization camera. And this camera is passive. It works both indoor and outdoor. And it is general. It handles both diffuse and specular materials. And those are the co-authors of this paper. And thanks for your attention. Next, I will show a video, and you can ask the question.
Thank you, Lawin. Are you going to do a demo right now, or?
Yeah, you can ask the question as well.
Okay, all right. Well, if there are any questions, please come up to one of the two mics on the two ends of the hall. So one of the most impressive attributes of your algorithm is the ability to handle specular objects, right?
Yeah.
If we take it to the limit, how specular can it be? I mean, the examples you show are quite promising, but can it handle mirrors? Can it handle complex objects like hair or the eyes?
Well, the hair is very precisely small, so small objects. I think it will be much harder if you use the current camera. So the resolution is very low, which makes the detail may somehow lose its detail. So I think it has some improvements over the camera. So if the camera could handle have a larger resolution, it will have some improvements over that kind of details. Yeah.
And how about mirror-like surfaces or surfaces which are more highly specular?
I think the polarization, if that one has more specular reflections, so which means if we observe by using a polarizer camera, so it can fit a good phase angle, which means it can recover the surface normal very well. So in that case, I think this algorithm, the way that 3D reconstruction by using the polarimetric will somehow get bigger improvements of that object compared to the conventional and multi-view stereo.
Yeah, thank you.
Thank you. We have a question?
This is very interesting work. Thanks for the presentation. And I would like to ask, do you assume the sim is static?
Pardon?
Do you assume the sim is static, like the object is no moving? And
Yes, we assume the object is moving, so the fusion as well as depth estimation is assume the object and scene is static. So in the future, we may try the dynamic scene, which we require additional works on to build a more powerful constraint for detect the emotions as well as the smoothness for the object reconstructions. Thank you.
Thank you.
Yeah.
Hi, this is very nice work. A question about dark regions. So in addition to featureless regions, dark regions are difficult for reconstruction. Will the polarization, I suppose, will also make that problem worse? Do you have any comments on that?
For the dark region, I think it's a very challenging cases because this camera is is a passive camera, which means it requires the additional light source to shade the lights on the objects. Otherwise, if it was a dark room or dark objects, I think the camera may be challenging thing for this algorithm to build a reasonable reconstruction result.
And another question, is the camera that you're using a custom camera or off the shelf? I do remember seeing a polarization camera here.
So right now this camera is you can buy it, but was very expensive, and it has so many limitations. So I think it will be improved in the futures.
So one of the things that I saw in the exhibit hall in the conference was a polarization camera using wire grid technology with multiple polarization angles, almost like a Bayer pattern per pixel.
Yes.
Do you think that kind of camera would be useful for this work?
Yes, I think so. So I also come to their places to see their polarization camera. So their polarization camera is be much better if it has more smoothness compared to the one we used. So I think it will be much better. I know the Sony has a new sensor for this types of camera, so which means it will be large used in the futures.
Sorry, in the interest of
staying
on time, let's thank the speaker one more time.
Thank you. Thank you.
So it's been an interesting session. We've seen learning make more of inroads into 3D vision and a look at the use of new sensing modalities as well. So let's thank all the speakers one more time and then allow the spotlight speakers to come up. Thank you.
Good morning, everyone. My name is Guillermo Gallego, and today I am presenting a unifying contrast maximization framework for event cameras with applications to motion, depth, and optical flow estimation. The past 60 years of research have been devoted to standard frame-based cameras, but they are not good enough, especially in low latency, high speed, or high dynamic range scenarios. Event cameras can solve all these problems. So what is an event camera? An event camera is a novel sensor that only output intensity changes asynchronously. And these are represented as a stream of events with microsecond resolution. They also have very low latency, no motion blur, and a very high dynamic range. However, traditional vision algorithms cannot be used on these sensors. And so we present a unifying framework to solve several computer vision problems with event cameras, such as optical flow estimation, ego motion estimation, and 3D reconstruction. We show how the same way of processing the events can be used to solve all these problems and unlock the potential of event cameras. Here we see a space-time volume of events captured by the camera. The main idea of our framework consists of warping the events to maximize the contrast of the resulting image. In this example of feature tracking, events are warped according to different velocities until the image that you see projected on the screen is sharpest. Let us show some applications of our framework, such as 3D reconstruction. On the right, you will see the input events of a desk sequence. Our framework estimates depth by selecting the regions with maximum local variance in this disparity space image, which is built from the events. Here we show a point cloud of the reconstructed scene, colored according to depth. Our method can be applied to obtain 3D reconstructions from a train moving at high speeds. In this example, we exploit the high-speed capabilities of event cameras to reconstruct the edges of the building facades and the trees around the train. Our framework can also be applied to enable high-speed visual odometry. In this example, the camera is attached to a string, spinning like a cowboy, which is one of the hardest scenarios for visual SLAM. We can track event features and use them to recover the 6 degree of freedom pose of the camera, which would not be possible using a standard camera due to motion blur and low dynamic range. Our framework also enables autonomous drone flight in low light. In the example, we extract features and we use them to estimate the pose of the drone, which is flying in closed-loop control. We switch off the lights, and while the standard camera cannot track the features, the event camera still can due to its very high dynamic range. To conclude, event cameras promise to revolutionize computer vision by unlocking scenarios that are currently inaccessible to standard cameras, such as high dynamic range, high speed, and low latency. They open opportunities in AR, VR, automotive, drones, and the Internet of Things. And we present a unifying framework that allows to address multiple computer vision problems with event cameras. I look forward to meet you at Poster E20 and also at Poster J22, where we combine event cameras with learning for autonomous driving. And we also have SLAM demos in the afternoon. Thank you very much.
Hello everyone, I'm Timur and I'm going to present our work on modeling facial geometries with compositional variational autoencoders. So one standard way to create models for facial geometries is to use global models, which are typically based on PCA. And the goal is basically to come up with a linear basis that essentially spans the space of all possible facial deformations. And one straightforward observation that we can make is that these kind of models can actually be seen as a form of shallow autoencoders. And the process of model fitting in this context that essentially means that we throw away the encoder, fix the decoder weights, and then we optimize the latent vector based on the given constraints. The main drawback of these kind of models is that they typically tend to struggle when capturing local high-frequency deformations. So that's why there's an alternative class of models which is more flexible, which are local models, where we have an independent set of parameters for different parts of the face. And similarly to the global models, the goal here is essentially to learn the deformation basis, but the difference here is that we learn them for patches rather than the entire face. And the main insight of our work is basically just like the global models, the local ones can be seen as a special kind of autoencoders, but in this case, they're shallow convolutional autoencoders. And well, given that the existing models are both shallow autoencoder networks, our key intuition is that we can come up with a more generic formulation using deep autoencoders. So the idea is that similar to the global models, the lower layers from the narrow part of the autoencoder will actually capture basis for global detail, and the higher layers from the wider part will capture basis for more local high-frequency deformations. However, just training deeper autoencoder is not going to work nicely, and there are two reasons for that. So the first reason is that we essentially do not have any kind of prior on the latent space, which makes optimization over this space harder. And the second reason is that we essentially rely on a single bottleneck representation, which makes it hard to capture high-frequency detail. So to solve those issues, we introduce a model which we call compositional VE. The main idea is essentially that we introduce multiple layers of hidden variables. And intuitively, we want the lower layers to capture global detail, which means that as we traverse the space, it changes the identity and the general expression of the person. And at the same time, we want the higher layers of variables to capture high-frequency deformations, such as wrinkles and facial hair. Then intuitively, the goal of the encoder is to decompose the input geometry into multiple layers of variables. And then the decoder essentially combines those variables back together and produces the final reconstruction. So the overall architecture then can be seen as a UNet-like architecture with probabilistic skip connections. It essentially means that in practice, the encoder and decoder is stochastic, just like in a classical variational autoencoder, and the encoder produces the distribution parameters for each layer of variables. And then the decoder effectively samples from those distributions to obtain the final reconstruction. And because of this variational formulation, the space is actually naturally much more suitable for optimization, which we need for fitting. So here we compare our compositional VE with global and local models for a task of depth fitting. And unlike those baselines, we were able to capture much more detail without introducing additional artifacts. And actually, one of the key features of our model is its ability to decompose geometries into different levels of deformation. So here we interpolate high-frequency detail between two different people while keeping low-frequency detail fixed. And you can see that the overall expression does not change while the beard is transferred successfully from one person to another. Well, in general, the model can be used for a lot of different applications. And for more information, please come by our poster, which is F1. Thank you.
Hello, this is Jae-sik Park. I'm going to introduce tangent convolutions for dense predictions in 3D. This is joint work with Maxim Tavtachenko, Vladlen Colton, and Chinijo. The problem we are dealing with is semantic segmentation of 3D data, where each point gets assigned to one of the classes. We focus on developing an efficient algorithm which can be applied to large-scale indoor and outdoor scans with millions of points. Motivated by the fact that the most real-world 3D sensors record surface data, we propose a novel convolution operation called tangent convolution, which operates directly on surfaces. It supports efficient implementation and is used as a core building block of a convolution network for large-scale scene analysis. Consider a 3D scan represented as a point cloud, which we want to analyze using a CombNet. The main idea behind our method is to locally approximate the surface geometry with a plane and compute regular 2D convolution in this plane. For each point in the point cloud, we define a tangent image and project the local geometry onto it. The orientation of the tangent image is determined through local covariance analysis. Such images are densified by interpolating signals from scattered point projections. The resulting dense images can be convolved in 2D with CombNet filters, yielding feature embeddings for each point. The main highlight of our approach is that it supports a simple yet very efficient implementation. The structure of tangent images, or the domain for computing convolution, is pre-computed in advance. For a scan with approximately 125K points, this computation takes about 1.5 seconds. The inference is done in a single fold pass and takes 0.5 seconds. The memory footprint of the corresponding network is 2.35 gigabytes, which easily fits on most modern GPUs. Same as conventional convolution network, our framework supports pooling and unpooling to increase the receptive field size. In our work, we use the UNet-like network architecture with two downsampling of sampling of operations and skip connections. The same architecture was used throughout all experiments. Here are main results. We evaluated our approaches on two indoor and outdoor datasets and compared with three existing approaches which operate on different representations of 3D data. For example, PointNet on point cloud, OctNet on octrees, and ScanNet on voxel grid. The table shows that we achieve strong results across different types of scenes and various input signals. So this is the comparison with different approaches, and this is the real example of indoor scenes. And this is an example of town scale outdoor scene, which is captured by the LiDAR scanner outdoor. Please visit our poster to check out the details. Thank you very much.
Hi, I'm Despina Pasalitou from Max Planck Institute for Intelligent Systems, and today I would like to present RAINET, our end-to-end trainable architecture for 3D reconstruction. 3D reconstruction is the task of estimating the 3D model of a scene given a set of images and their corresponding camera poses. It is a highly ill-posed problem due to large ambiguities introduced by appearance variations and occlusions from different points. Recent advances in deep learning gave rise to various methods that learn the multi-view stereo matching from data. While these approaches are able to learn robust feature representations against surface variations and different illumination conditions, they yield only 2.5D reconstructions. These depth maps need to be subsequently fused into a full 3D models using various post-processing steps. On the contrary, ray-based 3D reconstruction methods allow for full 3D reconstruction by taking into account the image formation process. However, these methods are restricted to very simple photometric formulations, and as a result, they fail to cope with complex surface variation. To this end, in this work, we propose RAINET, an end-to-end trainable architecture that combines a CNN that learns surface appearance variations across different viewpoints with an MRF that explicitly encodes the physics of perspective projection. In detail, RAINET is learned end-to-end using empirical risk minimization. Errors are back-propagated to the CNN based on the output of the MRF. This allows the CNN to focus on learning view invariant representations while explicitly incorporating the perspective geometry and occlusions. By back-propagating the gradients through the unrolled MRF, we update the weights of the CNN using the geometry of the entire scene and not just the appearance of a single patch. In detail, RAINET integrates an image-based CNN that learns multi-view image similarities and predicts a per-pixel depth distribution in a voxel grid. Due to the local nature of the extracted features, the per-pixel depth distribution estimated by our CNN is typically noisy. Our MRF aggregates these noisy depth estimates by exploiting occlusion constraints across different views, thus yielding significantly improved depth predictions. Our MRF is defined in a voxel grid where every voxel is associated with a binary occupancy variable indicating whether this voxel is occupied or not. Traditionally, occlusion constraints are encoded using high-order array potentials. However, in contrast to previous work, we do not reason about the surface appearance within the MRF, but instead we incorporate the depth distributions as estimated from our CNN. Computing the exact solution in a high-order graph, such as our MRF, is NP-hard. Therefore, we use sum product belief propagation for approximate inference. This is a message-passing algorithm between variables and factors. RAINET improves over learning-based approaches that do not incorporate multi-view geometry constraints and over model-based approaches that do not learn image features in terms of accuracy and completeness, both in indoor and outdoor datasets. In contrast to our baselines, RAINET yields sharp boundaries and significantly smoother reconstructions in challenging regions where our baselines fail, such as facades made of glass or other highly reflective materials. Besides, on the outdoor aerial dataset, we also evaluate RAINET on various objects from various materials from the DTU dataset. RAINET consistently improves both qualitatively and quantitatively over other existing approaches. If you would like to know more about our work, please come to our poster F7. Thank you very much for your attention.
Good morning, everyone. My name is Hiroharu Kato. I'm from the University of Tokyo. Today, I'd like to talk to you about our research regarding neural 3D mesh renderer. This work is done with Professor Ushiku and Professor Harada. Projecting 3D scene into 2D image is one of the fundamental functions of our vision. In modeling visual systems using neural networks, incorporating this projection into them is effective because 3D scene and its hidden dynamics can be optimized by backpropagation. And with this motivation, we developed a projection module or renderer for neural networks. By the way, what is the most preferable 3D representation? Voxel is a popular choice. However, handling high-resolution 3D model is difficult because of its memory inefficiency. Point cloud is another popular choice. However, textures cannot be used because they have no surfaces. Polygon mesh composed of sets of vertices and surfaces is the best choice in terms of memory efficiency and textures. So we adopt polygon mesh in this work. Defining backpropagation of mesh renderer is not so straightforward. Look at this triangle and a pixel. If the vertex X moves to the right and hits the pixel P, the color of pixel P suddenly changes to the color of the triangle, as shown in graph A. So the derivative of P with respect to X is 0 almost everywhere. To overcome this problem, we replace the sudden change with an invisible gradual change, as shown in graph B. Using our renderer, we can train single-image 3D mesh reconstruction without 3D dataset. A 3D reconstruction network is trained using silhouette images rendered from multiple viewpoints. This is the result. Compared to existing voxel-based approach, our method enables more accurate and visually plausible and favorable reconstruction. Reconstructed mesh has no cubic artifacts like voxels, and the accuracy is superior on ShapeNet dataset. Another application is 2D to 3D style transfer. Using the standard style loss of 2D images, a style of 2D image can be transferred into 3D object through rendered image by backpropagation. These are results of a teapot and a bunny. Look at the lid of the teapot. Not only textures, but also shapes are transformed along the style image. We also use a renderer for deep dream of 3D object. A bunny and a teapot are transformed into these ugly figures. Our renderer can be used for many other tasks. The code is publicly available. Please try it if you are interested. Thank you for listening.
Good morning, everybody. My name is Dan Xu. I present structure attention-guided convolutional neural fields for molecular depth estimation. Molecular depth estimation is a task that recovers depth of the scene by giving one single RGB image. It has been shown in particular useful in various computer vision tasks. Structure prediction is a common strategy in molecular depth estimation. In the basic framework of structure prediction in single scale, the self is modeled on the input RGB image, and then it's used to refine the cost depth output produced from the backbone CN. A representative work in this track is deeper convolutional neural fields. The structure prediction in multi-scale can be also performed in multi-scale setting. A representative work is multi-scale continuous self as CNN. However, in the existing works, they mostly focus on the prediction level, which brings less flexible in modeling due to the more strict definition of the kernels, and also produce more loss on the structure information while the network goes deep. So in this work, we aim at designing a model working on intermediate feature level and utilizing an attention mechanism as guidance for the feature learning. To achieve this target, we designed this framework. It consists of encode and decode and a proposed structured attention-guided multi-score feature learning model. Now we give the details of this proposed model. Given a set of latent attention maps, A, and a set of latent feature maps, Y, the CF model can be defined with another function E as follows. The first term defines a unary potential between the observation and the latent feature variables. And the second term defines the pairwise potential between the attention variables and the latent feature variables. The latent attention variables are binary to control the method passing between the latent feature variables. The last term defines the pairwise potential between the latent feature variables. So we approximate the inference of the whole model. We approach the inference of the CF model with a mean field theory, and iteratively perform the mean field updating for the latent feature variables and the latent attention variables. The whole model is implemented in CNN to enable end-to-end optimization. The attention maps are learned. The attention maps learned from different scales show significantly spatial variance. We demonstrate the results, the experiments on V2 datasets. Here are some examples. Quantitatively, our approach achieved the best performance compared with approaches trained on the standard training set. We also conduct experiments on the KT data set. We compared with the state of the art on this data set. Our approach produced more fine predictions. And in terms of the quantitative results, our approach achieves the best performance compared with the approach in the setting of molecular depth estimation from one single image. Thanks. Welcome to our post for more details. Thank you.
We often see in the indoors images with normal field of view, where the whole room information is largely missing. Therefore, you may want a 360 view of the room. However, it's not enough. So we are seeking to generate 3D structure of the whole room. Our method aims at collecting 2D panoramic representatives to estimate accurate depth for both background layout and foreground objects. Next, let me introduce the details of each representative and explain how to use them to infer 3D depth. Starting from the pre-processing step of our Q extraction. Our Q extraction starts from sampling the panorama image into local perspective subviews. After that, we apply the object detection saliency estimation to each subview for the semantic Q extraction, and line detection a geometric context for the geometric cues. Saliency detection helps when object detection fails due to the object occlusions. To separate the layout from the object for a separate analysis, we further define the energy function and then solve it with the binary label graph cut. Similar to reference method, we also apply the line segment detection method to detect lines from the panorama. We initialize the ground region with the pixels that are labeled as the ground by the geometric context. We then use the surface normal maps as the seeds to propagate the ground region. To solve this problem, we explore the connection constraints and the coplanar constraints between the superpixel to superpixel, line to line, and the line to superpixel pairs. We use normal consistency and object region prior to locally calculate the possibility of each assignment for each line. T-junction is also being used as evidence of occlusion. We deem two superpixels are connected if no occluding lines intersect between them. We also deem line and superpixel to be connected if superpixel is not on the occluding side of the line. We conduct the coplanary constraints by calculating the intersection between each pair of lines. After we get estimation of layout depth, we infer the object depth by propagating the depth information from layout. We compare our method with the state-of-the-art with the error map and the depth cosine errors. Left table shows the performance corresponding to each Q extraction, while the self-evaluation results are shown in the right table. Despite a large number of superpixels in our segmentation map, our depth map has better details. We show the reconstruction results with the shaded mesh and two virtual wheels. The different virtual wheels also show how well the object depth has been extracted. However, our technique can fail if the object mask incorrectly localizes the object and misleads the normal maps. Thanks. Please come to our poster section for further questions.
Hi, everybody. Today, I want to introduce our work of extreme 3D phase reconstruction, seeing two occlusion. We are from University of Southern California and the Open University of Israel. This is the first accurate, detailed 3D reconstruction of faces in the Y, and we can do so even under occlusions. Given this input image, it is a man with a lot of details like wrinkles, and he had occlusion due to the glasses. We want to recover his detailed 3D face without the glasses. So it is very challenging, right? Okay, so now see how the state-of-the-art methods work. The first type method directly estimates the face depth from the input image, for example, Sela in ICCV17. You can see that it can recover the details of the face. However, the mask is distorted due to the glasses. Also, you can see that the eyes are bad. And the mask is incomplete due to self-occlusion. The second type method is model-based. For example, Chang in CVPR18. In this type of work, people try to fit the face in the input image into a 3D morphable model so that we can get a complete face without occlusion. However, it cannot recover the details like wrinkles, so the face looks smooth. Okay, now let's see how our method works. You can see that we can remove the glasses, so now you can see clearly his eyes. Also, our model is complete. You can see both sides of the face. And we can recover the details like wrinkles. So the key idea is that we need to decouple robust foundation shape estimation from detail estimation. How can we do so? Given this input image, first, we need to estimate the foundation shape using the model-based methods. And then we estimate the details in form of a 2D bump map using a deep network. And then we combine them together to get a detailed mesh. You can see that this mesh still had occlusion. I mean the glasses here. So we need to detect the occlusion area. And then we use an example-based method to select the closest example in a gallery and combine with the current mesh to get the occlusion removed. And finally, we apply symmetry to get a complete face. And this is the final result, which looks very good. Okay, now let's compare our work with others. Given this input image, which is rotated and he had glasses, we can recover his complete face without the glasses. And you can see his skin details. CVPR17 method returns a smooth face. And Sela method returns an incomplete face which is distorted due to the glasses. Here is another example. In this, we have a hand covering the mouth, but we can recover his detailed face without the hand. CVPR18 method again return a smooth face. And Sela method return a distorted face in which you can see clearly the hand. And we also have a lot of great other examples like this in our paper. Our code is available online, and please come to our portal F19. Thank you.
Hi, I'm Victor Larsson, and I will be presenting the paper Beyond Gröbner Basis, Basis Selection for Minimal Solvers. So this is a joint work with Kalle Åström, Magnus Oskarsson from Lund University, Alger Wallis from University of Bath, Susanna Kukulova and Tomáš Pajdla from the Czech Technical University in Prague. So we are interested in solving systems of polynomial equations. These equations typically come from the minimal problems in geometric vision, where they're used in ransack framework for robust estimation, or to otherwise bootstrap some local optimization. For these methods to be useful in practice, the runtime is very important. Generic methods for solving polynomial equations are in general too slow. Instead, we use so-called minimal solvers, which is specialized code for solving each problem. And ideally, we want to spend less than 1 millisecond per instance. So, most minimal solvers in computer vision try to convert the equation system into an equivalent eigenvalue problem. For the eigenvalue problems, we have good numerical methods, so we can solve them. The minimal solvers typically work in 2 steps. First, you need to solve a linear system to recover the action matrix, and then you recover the solutions by computing the eigenvalues. The size of the eigenvalue problem depends on the number of solutions, and this is typically fixed for each problem. So to try to reduce the runtime of the solver, we can only try to reduce the size of the linear system we need to solve. So in the eigenvalue problem, the eigenvector b contains monomials which forms the basis for the quotient ring. These are usually taken from a Grevlex-Gröbner basis, since this has been empirically observed to give small solvers. The main idea in this paper is to instead try to choose this basis to try to minimize the size of the linear system, and thus also the runtime of the solver. So each Gröbner basis gives us one basis for the quotient ring. And it turns out that for each problem there are only finitely many different Gröbner bases. So one idea we try in the paper is to just enumerate all of the different Gröbner bases, build a solver using each one, and then take the best one. The graph shows an example for the P4PFR problem, where we have built a solver using each possible Gröbner basis. For this problem, the best Gröbner basis solver was more than twice as small as the original Grevlex solver from the paper. However, the basis does not need to come from a Gröbner basis. This is an arbitrary constraint. In the paper, we also propose a random sampling scheme to select the basis. The sampling is guided by some different heuristics, which we have observed to give small solvers. The graph again shows the P4PFR problem, where we have sampled different solvers, both with and without the guided sampling. We can see that uniform sampling produces very poor solvers. So here we show some results on a bunch of different minimal problems, mostly relative pose problems, where we have done exhaustive search over Gröbner bases as well as this random sampling approach. And we can see that for most problems, the random sampling approach gave smaller solvers compared to the best Gröbner basis-based solvers. So thank you for your attention. If you have any questions or comments or want to talk about minimal solvers, please come by the poster. The code for this is available online. Thank you.
Good morning. My name is Silvia Zuffi, and I will present lions and tigers and bears capturing non-rigid 3D articulated shape from images. And this is a joint work with Andrew Kanazawa and Michael Black. So the goal of our work is to create 3D models of animals from images. And this has many applications, ranging from entertainment to robotics to biology and more. But for most of the animals, it is hard to capture 3D models with current scanning technologies, because animals can be wild or because animals can be extinct. And this is indeed the video of the Tasmanian tiger that became extinct in the first half of the last century. So creating 3D models of animals from images is very hard. And previous work has done it for dolphins, bears, cheetahs, cats, giraffes, and more. Template-free approaches produce results that have limited realism, while template-based methods did not exploit multiple images of the same subject for an accurate recovery of the animal shape. So in our approach, is to make the problem simpler by exploiting recent advances in animal modeling, and specifically we use a 3D articulated shape model that can generate 3D shapes from 5 different families, like horses, big cats, cows, dogs, and hippos. So we want to exploit the large number of images and videos of animals that are present, for example, on the web. And suppose we have images of an animal taken at different moments from different views. So in all these images, the pose and maybe the camera are different, and what is constant is the animal shape. So in our method, the input is a set of images where the animal is seen from different views. We annotate the location of body landmarks and generate the animal segmentation masks. And then we fit a small model to each image, exploiting the landmarks and the segmentation. And we jointly optimize over pose, shape, and camera parameters, adding the constraint that the intrinsic shape of the small models is the same for each image. So this gives us a good initialization, but it is not enough. The small model has been learned from a small set of 3D scans of animals and cannot generate fine shape details. So therefore, we perform a refinement step where we improve silhouette and key points matching, optimizing over the mesh vertices. And this is a high-dimensional problem, so we impose smoothness and symmetry to regularize the solution. Our method is called smaller for small with refinement. So with smaller, we obtain a better fit to input data and also capture the animal texture. We applied our technique to different animals, recovering shape details that are not present in the small model, like, for example, the rhino's horn. And we were also able to recover the 3D model of the Tasmanian tiger. So compared with previous work, we obtained more realistic results. And we 3D printed some of the animals. You can see these ones and more at the poster G3. And the models are available in Sketchfab or on the project website. Thank you for your attention.
All right, thank you all for coming. That concludes the session. Let's thank the speakers one more time.